Hadoop enables the distributed processing of large datasets across clusters of servers. Hadoop clusters can dynamically scale up and down based on the available resources and the required service levels. Let's show a traditional Hadoop cluster. The components are the name node, secondary name node, and data nodes. The name node holds the metadata or the location information for every file in the cluster. There is also a secondary name node that is a backup for the name node. The secondary name node is passive. As the name implies, the data node is where the data resides. Data is spread across the nodes with a 3x mirror. A logical compute process runs on each data node, handling compute operations such as MapReduce that runs analytic jobs. In a traditional Hadoop-only environment, the HDFS is a read-only file system. As you can imagine, it would be difficult to do an analysis on a dataset that constantly changes. Typically, Hadoop data exists in silos. Production data is maintained on production servers and then copied to a landing zone server, which then imports or ingests the data into HDFS. It is important to note that the data on HDFS is not production data. It is copied from another source. Where does the Isilon fit in this solution? Implementing Isilon allows the production data to reside on the Isilon cluster, so there is no need for a landing zone or exporting it from the production environment. The MapReduce continues to run on dedicated Hadoop compute nodes. Isilon requires the Hadoop front-end to do the data analysis. Hadoop compute clients can connect to any node on the cluster that functions as a name node instead of being routed by a single name node. The Hadoop clients connect over HDFS to access data on the Isilon cluster. Windows, Linux, and Mac OS X clients still access the cluster over SMB, NFS, FTP, and HTTP. HDFS connections are made up of two separate connections, a name node connection and a data node connection. For data node IP allocation, the name node gets all the IPs in the access zone, in this example, the Hadoop access zone. Next, the name node looks at the rack configuration and gets the IP addresses for the rack. The name node also checks if any IP addresses are blacklisted. Then the name node gives out rack IP addresses first based on client IP. Otherwise, it returns IP addresses across the entire zone. Data node load balancing is an Isilon feature that allocates IP addresses from a name node. The IP addresses given when metadata is requested is from the nodes that have the lowest connection count. When a client sends a request to write to the cluster, Isilon's pipeline write recovery feature provides 3 data node IP addresses to the client. If the first node shows any issues, the client will use a second and then a third IP to finish their Hadoop jobs. This provides an automated retry for clients. Data node load balancing and pipeline write recovery fixes issues where a data node runs out of threads. Features are available in 1FS 8.0.1 and later. In closing, there are 2 top known issues with name node to data node IP address allocation. First is when there are multiple access zones for HDFS, the name node can give out IP addresses from a different access zone. Second, opening multiple security contexts can cause the error status too many files open. All data nodes are bad errors. The pipeline write recovery feature fixes the security context issue.